Hi everybody, this is Dr. Bricker here with a video for chapter 23, which is about circuits. This is part 1. Okay, so this is kind of a continuation of the previous chapter. The goal is to understand fundamental physical principles that govern electrical circuits. We've already kind of seen some of them. We've talked about resistance, current, voltage, so we'll continue with that and we'll put them into something called actual circuits. And we've seen, again, something called a simple circuit before. It's just called a simple circuit because it has a battery, a resistor, and just one resistor, one battery. So we'll get a little bit more complicated in this chapter. And we'll come back to this electric eel in just a moment. Okay, so circuits consist of many different elements. We've talked about resistors before, batteries. This is what will provide the potential difference. We've talked about capacitors. Now we're going to put them all together in a circuit. So what you see here are resistors in the picture that I'm highlighting, connected by wires. We've talked about wires before, and different circuit elements. This is probably a capacitor here. Okay, so lots of different parts. These are capacitors for sure, these blue devices here. So we'll be able to analyze some more complicated circuits. So there's two basic kinds, series and parallel. So in your house, circuits are connected in parallel. Series circuits are the kind of circuits where you go from one light bulb directly to another light bulb, directly to another light bulb. So holiday lights sometimes are wired in series. So if one bulb goes out, the whole strand is out. Or else they're wired in parallel, where if one bulb goes out, the whole entire strand does not go out. We'll see the difference between those. Okay, it says down here, you know, holiday lights are wired in series. They're not all wired in series. More and more it seems like they're in parallel. Headlights are not wired in series, though. You wouldn't want one headlight to go out and then automatically the other one goes out. So those are in parallel. So just like your house, if one of your outlets for whatever reason trips a breaker, the rest of your power in your house still works. That's not on that circuit anyway. Okay, if you're in biology or interested in biology, your nervous system works sort of like circuitry, if you think about it. So electrical signals are sent along, or transmitted, it says here, along axons, which are nerve fibers. So you'll learn how to understand nerve impulses in terms of resistance, capacitance, electrical potential. So electrical potential across cell membranes, things like this. Okay, circuit elements and design. So in a minute we'll have just symbols to represent these different elements, but here's a resistor. This is what it might actually look like. The color coding tells you the resistor value and the tolerance. Or capacitors, which might look like this for a parallel plate capacitor. The center part here is a battery. So instead of having to draw these out every time, we'll have different symbols that will just stand for these things. So one of the labs you'll do, you'll actually build circuits with just these sort of a diagram way of looking at it. Okay, so rather than, again, drawing a literal picture, we can use a circuit diagram. So if you end up doing a lot with circuits in your career, there's programs that will actually build these things for you, and you can put them together that way. Okay, so circuit's just a logical way of laying everything out, so you don't have to literally draw all the different elements. Okay, so a battery, here's the symbol for battery. The longer part is the plus side, the shorter part is the negative side. A wire is just a straight line like this, or you can curve it if you want to. A resistor has this shape. Okay, good, so we'll use those when we draw some circuits. Light bulb you could represent like this, junction of a couple of wires coming together. Capacitor, these are equal lengths, this side and this side. The difference with the battery is a battery has one side longer than the other side, where the long side is the positive side. Or you could have an actual switch here too. Okay, so what's represented here is in this picture. This is the actual devices. Here's how you could draw it as an actual circuit. So if you think about it, here's the battery. So from the battery, current could go one of two different ways. It could go this way, or from coming out of the battery, it could go that way. So we could represent this circuit in this way. There's a lot of different ways of representing it, but this would be one way. We're assuming here that the wire doesn't have any resistance, So current comes out of the battery, then it could go one of two ways. It could go down this way, or it could go this way. Just like in the picture up here, current could go this way or this way. Okay, it takes some getting used to. It seems like the capacitor in this picture is farther away from the battery, and in the picture it is, but electrically speaking, if wires don't have any resistance, you could make this wire going into the capacitor as short as you want to. Maybe a better way of drawing it would be like this. Let me switch to pen mode real quick. Okay, pen. So the circuit that you see here, you could draw just like this. Battery, battery comes out. You could have a resistor here and a capacitor here, and then they can come back together, go back to the battery. So what I've drawn down here is the exact same thing. Current comes out of the battery, then it splits off. It could go this way or it could go that way. Just like in the top picture, current could go one way or the other way. Okay, so what I drew here in the red is the same exact thing as what's being drawn in this picture here. Usually with the battery, I'll just do a long side and a short side. The book does long, short, long, short. It's the same exact thing. Okay. So Kirchhoff's law, and you've already seen this before, he has a couple of laws. This is the junction rule. So we saw this back in the previous chapter. Whatever goes into a junction, so I1 goes this way, has to be equal to whatever goes out. So I3 and I2. So I1 has to be equal to I2 plus I3. Again, we've got some practice with this before, but we could use this to help us analyze some different circuits. Okay, good. So if you go around a circuit, whatever voltage the battery is applying, or the battery has, is utilized going through these different elements. So in the ski lift analogy, so from point A to point B, that's the ski lift. It gets us up to some height. Now we're assuming that these wires don't have any resistance. In real life they do, but relative to everything else in the circuit it's small, so we're assuming it's 0. So to go from B to C doesn't take anything because it's at the same level. And then when you go through the first resistor, you have a voltage drop. This is going downhill now. And then between the resistor, point D, there's no voltage drop. And then from this point, from E down to, going back down to E, so from D to E, you have a voltage drop. So let's recap. From A to B, this is like the ski lift. B to C doesn't take anything because it's a wire and we're assuming it has no resistance. And then from C to D, this is where the battery actually does something. So you use some potential here. Between the resistors, nothing is used. And then from D back down to E, that's where you actually go through something. And then you go back to this side and the ski lift lifts you back up. So this is conventional current flowing this direction. Okay, so this is a series circuit. The same current goes through this resistor, the same current goes through this resistor. So as it says here, this is a way of writing Kirchhoff's voltage loop. Basically what it is saying is what I've just said here. This does something for you. This is kind of thinking about going downhill and going downhill. This lifts you up, down, down. So however much you lift it up is got to be equal to however much you go down. So battery lifts you up. These resistors are using it up. Not literally using up electrons or anything like that, but that potential that you have goes somewhere and it goes into driving the electrons through these resistors. Okay, so that's just, this is a fancy way of writing that, this Kirchhoff's loop rule. Okay, so as you go through each circuit element, delta V can be interpreted in a few different ways. So let me, it says my take here, let me show you what I mean by that. Okay, so here's a picture of a voltage source, squiggly E for that. Current comes out of the battery, goes through a couple of resistors, and so here's I going this way, back through this resistor, and then, you know, back to the battery. Same currents. So this is my take on it. So the battery does something for you. So this side is minus, this side is plus. So let's just go around this circuit this way. So I encounter the battery. negative side to positive side. That does something for me, so I think of that as plus E. Then I hit this resistor, plus to minus, minus V1, and then I hit this resistor, plus to minus. So you put minus V2, and then I'm back to the other side of the battery. So I've gone around this circuit. EMF of the battery, and then with the battery, think about it like this: minus side to plus side. It's raising up a charge, like the ski lift. You go through a resistor, plus to minus. So then we are using some of the voltage of the battery. So you write minus V1, you hit another resistor, so this would be minus V2. That's a minus side, and it adds up to 0. So let me put V1 and V2 on the other side. V1 plus V2. So this is another way of looking at the formula. The voltage of the battery, that's what's doing something for you. Where does it go? Well, it goes to this resistor and this resistor. So you lift it up to some height, and then you go down a couple of hills. That's how to interpret this formula. So don't forget, Ohm's law that we saw before still works. So V1 would be equal to I times R1, and then V2 would be I times R2. Okay, very good. Let's get back to the PowerPoint. So as it says here, delta V battery, that's what the squiggly E usually is, can be positive or negative for a battery. It depends on which way you're going around the circuit. But delta V for a resistor is always negative because it's a potential, the potential decreases as you go across it. So it's called a potential drop usually. So when you hear the words voltage drop, or potential drop, that's what it means. You're going across a resistor. A lot of this stuff with circuits just takes practice too. Okay, so here's a so-called simple circuit. It doesn't mean like it's easy, it just means it has a battery and one resistor, so it's called a simple circuit. Okay, so here's the battery minus the plus. Current would flow out of the battery like this, and then go through this resistor. Okay, so no junction points, it's the same current all the way through. So whenever you have a series circuit, it's the same amount of current that goes through one element right into the next element. Okay, so the voltage of the battery, the squiggly E, where it happens to it? Well, it's utilized here in this resistor. So just from Ohm's law that we did before, this is I times R. Okay, so minus the plus, and then plus to minus. So whenever you're going from a minus to a plus, you think of that as a positive quantity. Whenever you go from a plus to a negative, you think about that as taking something away. Okay? So when you go all the way around the circuit, you're back to where you started. If you started at the ground level, the battery lifts you up, you go through a resistor, it takes you back down, and then repeat after that. So that's what this formula is saying here. It looks like, how could it add up to 0, right? It's because this one, the voltage across the resistor is negative. Okay, so the potential increases as you travel through a battery, and then you use it up going through the resistor. Okay, it's just like the ski lift. You're lifted up to a level, you have some gravitational potential energy, and you use it up as you go back down to the ground, and then you gain kinetic energy. So that's what's happening here, right? This electron that goes through here actually turns its potential energy from the battery into kinetic energy, and then probably heats up the resistor. It becomes thermal energy. Okay, very good. So Ohm's law will help us out with solving that. Again, that's what this is coming from, I times R. Okay, so this is using Kirchhoff's rule to go around that circuit that we just saw. Squiggly E minus I times R is equal to 0, going all the way around. So there's a step of algebra that's not listed here. Let me switch to that. Okay, so this, put the IR to the other side, and then divide both sides by R. That's where this is coming from here. Okay, and then you can figure out the current. So when you're talking about circuits, we'll have things like resistance, voltage, current. This is kind of a a macroscopic way of thinking about things. We thought about things in terms of individual forces between charges before, microscopic way in the beginning of the semester. Now we're into more of a macroscopic way. Okay, so here's an example we can take a look at, and we want to know how much this resistor is. Let me just call this one R. And we know how much current we have, 1 amp. And then I'll make a separate video for the homework question here. So what is the resistance of this element? So let me call this one R1 and R2, and actually maybe I'll just call this one R3. Let's try to figure out what R3 is. So this would be V1, V2, and V3, the voltage drop across that resistor. Okay, so squiggly E, let's analyze the circuit. Let's start at the battery and work our way around. Plus to minus as I go this direction, plus to minus, because I'm assuming the current is going clockwise. So the battery actually does something for me. That's the squiggly E. And then I would have minus V1, minus V2, minus V3. And then that's equal to 0. Now remember, each of these, like V1, would be equal to I times R1. So I actually know how much that is. V2 would be I times R2. So I know how much that voltage drop is. V3 would be I times R3. I don't know what R3 is, though, so I can't figure out V3 as it is. But I can do this. Squiggly E minus V1, which I'll know, minus V2 is equal to V3. So we can solve for V3. So this would be 9 volts minus V1, which is 1 amp, times R1, which is 3 ohms, minus V2, which is 1 amp. Remember, V is equal to IR from Ohm's law. So this would be 1 amp and then 2.5 ohms. That's equal to V3. And I'm running out of room here on the slide, but basically we have 9 minus 3 minus 2.5. I'll write this at the top. 9 minus 3 minus 2.5. That's equal to V3. So 9 minus 5.5, it looks like 3.5, right? So 6, 5, 4, 3.5, yeah. Okay, so that's the voltage drop across R3. Okay, so 3.5 volts, you know the current, so you can figure out what R3 is then. I'll leave that part to you, but you have V3, this is 1, you can figure out R3. Turns out to be 3.5 ohms, right? So 3 volts would be equal to 1 times something. The something here is 3.5 ohms then. Okay, now if you've taken circuit classes before, you could do this a lot faster than I just did it. I wrote every step out. Some people in circuits could probably just look at it and tell you how much it is. Okay, and then again, we'll do 23.5 on a separate video. So series and parallel. Series look like this. It's the same current, comes out of the battery, goes through one device, and the same exact current goes through another device. Parallel means it splits off. So if this is I, it's going to split off. This one could be I1, this one would be I2, and then the total current is I1 plus I2. Whereas in the series circuit, it's the same current. Right, it's the same current that goes through. So that's a difference between series and parallel. Series, it's the same current. In parallel, the current splits off. Okay, more about that in just a minute. So if these are identical bulbs, these would have the same brightness. So same bulbs mean they have the same resistance. Series, it's the same current, so they have the same voltage drop. They're the same brightness. And if one of these bulbs went out, the other one would have to go out too, right? By going out, it breaks, current can't get through anymore. So you wouldn't have any bulb lit up if one of them goes out here. Okay, same current again, so they have the same brightness because of the same kind of bulb. Okay, it's the same amount of power too then, I squared times R. going back to the previous chapter. So they take up the same amount of power. Okay, good. So series, same current. Okay, so I guess the way to think about this is like, why is A not brighter than B? Because A is there first, it's going to take up the current. It's kind of like if you had a couple of water turbines hooked up. Water went down a river, hit the first turbine. It doesn't use up the water just makes the turbine move, and then it hits the next turbine and moves the next turbine. So water's not used up. Just like here, current's not used up. It's the same amount of current. Okay, very good. So that's what they look like in series. The voltage of the battery is equal to the first voltage drop plus the second voltage drop. Sometimes people write delta V1 and delta V2. You'll probably just see me write V1 plus V2, and it's the same thing. It just depends on what you want to call them. Okay, good. So we've seen that before. Going around the circuit, all the voltages add up to 0. So in series, it's the same current, but the voltages add up. Current, same, but the voltages add up. V1 plus V2. Now it's going to be the opposite scenario with parallel circuits. Okay, so in this example, then you know the current is the voltage divided by the resistance if you put everything together. Okay, good. So let's see, how much is the current in the battery. We've got 12 volts to work with. From what you saw on the previous slide, maybe I can call this one R1, V1, this could be V2 and R2. You can figure out how much current you have. I mean, you could go through the whole thing, add these things together, you know, like you did, but we just did that actually. You can see it there. If there's two resistances, the current is just the voltage of the battery divided by R1 plus R2. Now if you had 3 resistors in series, you would just add an R3 at the bottom. So here we've got 12 volts divided by 18 ohms. So 2/3 of an amp in this problem. So it looks like choice D. Okay, good. Equivalent resistance is 18 ohms here. So when it says equivalent resistance, it means, what if you want to make this into a simple circuit? Right now it's not a simple circuit because we've got 2 different resistances. What if we wanted to take this and make it into a simple circuit? Well, when you have series, you just add the resistances together. So a 12 and a 6 in series you could replace with an 18. So when it says equivalent resistance, that's what it means. What would you have to do to just have one resistor? Okay, so that would be the same exact circuit if you had a 12 volt battery connected to an 18 ohm resistor. Then that's the same circuit. This more complicated one becomes that. Okay, so in series, to get an equivalent resistance, you just add the different elements together. This was only 2 resistors. If you had 3, 4, 5, as long as it's series, you just can add them together, as it says here. So what we're trying to do when we analyze a circuit is make it easier to analyze by making it into a simple circuit. Again, a simple circuit is just this. 1 battery, 1 resistor. So you can do that. You can replace a whole bunch of series resistors with just 1 resistor if you just add them all together. In parallel, it doesn't work out like that. Okay, so a string of Christmas tree mini lights consists of 50 bulbs wired in series. What is the potential difference across each bulb when the string is plugged into 120 volts? So if you've got 50 of them, they share the 120 volts equally. So each of them is going to have 120 volts, and we're going to have to divide it by 50, right? Each of them is using some fraction. So 12/5. Looks like about 2.4 or so. So 12/5, right? The zeros cancel out. 12/5 would be 2 and 2/5, and that's 2.4. Okay? As long as I did that right, it looks okay. 10, 12 fifths, so 2.4 volts each. So take 2.4 volts, multiply it by 50, and you should get back up to 120 if you want to check your work. Okay, so that's kind of a synopsis of what I've just done here. So they all add together, 2.4 volts each. Okay, great. So in series, the voltages all add up to the voltage of the battery. It's not going to be the same in parallel. Just a little bit of foreshadowing there. Okay, good. So when you compare two circuits, one with a single bulb and then the other with two bulbs, all the batteries are connected identically. How does the brightness of the bulbs in the different circuits compare? So if you think about it, this has two bulbs. So the resistance in the second circuit here is twice as much than this circuit. This only has one bulb. So the current here in the second circuit is going to be half as much. So these are going to be half as bright as this. It's because you've got to power two bulbs with one battery. Here because it's got the same current, here you're only powering one bulb with this in series. Okay, and this is a synopsis of what I've said here. That's the big part here. So these B and C are equally bright to each other, but they're less bright than A. So B and C are the same, but B and C are less bright than A. Okay. Again, we will talk about this in a separate video. So battery is source of potential difference, not a source of current. The current depends on the different elements we're hooked up to. So if you have a 12-volt battery, we don't know how much current it's going to provide. It depends on the circuit that it's connected to. Okay, so it doesn't have a set amount of current. It's not a set current amount. It's a set voltage, and then the current is determined by what it's hooked up to. Okay, good. So parallel looks like this. Current comes out, so it splits off. So let's call this one I1 and this one I2. Splits off, but then it comes back together, I1 and I2. So whenever that happens, we are in parallel. And again, we're assuming the wires don't have any resistance, so you could draw this any way you want to. And I'm just going to draw it over here so you can see. This is the same exact circuit. That doesn't look so great. Scratch that out, and let me draw it here. And then this is a whoops, this is a battery, or a light bulb, and here's another light bulb. Like that. Okay. Light bulb, back together. So this is where this picture is really emphasizing that it's the point where the current splits off. So you can take these wires and shrink them down, make them larger. My circuit is the same thing as that circuit. Let me do a better picture than that. Okay, so here's my couple of light bulbs, and this is the exact same thing that you see in the slide. The current is going this direction, and then it's going to split off. I1 and I2. And the wires don't have any resistance, so you can make them as big or as small as you want to. And then I is equal to I1 plus I2. So the current splits off, but then it comes back together. Okay. All right, back to the slides. Okay. So which light bulb is brighter here? Are they equally bright? So these are actually equally bright. It's the same amount of current going through each of them. These are identical bulbs, so again, the current comes this way, splits off. My picture really emphasizes this fact, but it's the same current going through each of them, so they're going to have the same brightness. Okay, so the potential difference at these 2 points is the same because there's no potential difference across the wire. So what it's saying here is this bulb looks like it's really far over here, but this wire doesn't have any resistance, this part here. So you can make that as big or as small as you want to. So these are going down the same hill, actually. So here's the ski lift analogy for this. The battery lifts you up to one point, and then you've got two different paths you can take. You can either take this path or you can take this path, but you're still going to end up at the ground. Whereas before with the what we did before in a series circuit, the ski lift lifted up one point, you went down one part of the hill, and then the same current went down another part of the hill. Here you have two different ways to go. So the ski lift is taking you up to the top. Here's the ski lift, the battery. Ski lift is taking you up to the top here, and then you've got one of two different trails to go down. You could either go down trail A or trail B. You end up at the ground. The ski lift takes you back up. Okay, so you got two different paths to go by. Okay, good. So you might think A would be brighter because it takes the shortest route, but again, you can make those wires as short or as long as you want to if they don't have any resistance, just like I did in that little picture. Okay, so they have the same potential. So the ski lift has lifted you up to the same height. You have the same potential. So you're at the same height here or here. Okay, so in parallel, you have the same voltage. So the voltage of the battery, the squiggly E, is equal to V1, and that's equal to V2. You're raised up to the same level. Now it's the currents that are going to be different. Right? This is the current coming out of the battery. This we'll call I1. This one can be I2, and it's the currents that add up. So the total current is I1 plus I2. So that's the exact opposite of series. In series, it was the same current, the voltage is added up. In parallel, it's the same voltage across each element. It's the currents that add together. Okay, as you can see in this is a better picture. Okay, so the current that's coming out of the battery is I1 plus I2, just like the picture. So how much is the current? Well, it's going to be I1 plus I2. That's the same thing here. This is I1. This term is I2, right? The current is the voltage divided by the resistance. Voltage divided by resistance, that's I1. Voltage divided by resistance, that's I2. You add them together. Now they have the same voltage because they're in parallel, so that's the squiggly E, and you could rewrite it like this. Voltage of the battery is E 1 over R1 plus 1 over R2. What we're trying to do is take this parallel circuit and make it into a simple circuit, and we can do that by what we have here. Remember, V is equal to IR, so then I is V over R. Okay, so that's what we have here. Here's V divided by something, and it's this inverse of this quantity. Okay, so in with a parallel circuit, you can get an equivalent resistance, just like we did with series. It's 1 over R1 plus 1 over R2. That's what the equivalent resistance is in parallel. I usually write it like this. 1 over the equivalent resistance is 1 over R1 plus 1 over R2. So in parallel, the overall resistance, the total equivalent resistance, is smaller than any of the individual items. So for example, let's just pretend that this is 10 ohms and this is 10 ohms. So you could take those two 10 ohms in parallel and replace them with one resistance. The equivalent resistance would be 1 over 10 plus 1 over 10. So 1 over the equivalent then is 2 over 10. And then you got to invert both sides, so the equivalent resistance is 10 over 2, which would be 5 ohms. I'll write the whole thing out. So you could take two 10 ohm in parallel and replace them by one 5 ohm resistor and make it into a simple circuit. So how could the overall resistance be less in parallel? It's because you give the current multiple ways to go. So in your house, if you keep plugging a whole bunch of things into an outlet and they're wired in parallel, you'll end up drawing too much current because the overall resistance is getting less every time you use it, because you're giving current more and more pathways to go through. Okay, good. So yeah, your house is wired like parallel. Good, so this is the formula. Again, I like to think about it like this. Either way is totally fine though. I guess I like my way because if it's the resistance are convenient, then you don't even have to use a calculator like I just did. Okay, again, we'll come back to these. So in parallel, the more and more things you put in parallel, the larger and larger the current becomes. So this circuit, the B and C are equally bright to each other, but they have a larger brightness than A over here. It's because this circuit here, the second one that you see, draws more current because the overall resistance is less. The overall resistance of the second circuit is less, so the overall current is more than in the upper circuit. So B and C are equal to each other but brighter than A. Okay, good. Maybe it's a little counterintuitive, but you just have to stop and think about it for a minute. Okay, so let's see. What things about the three resistors in the circuit are the same? Okay, so there's a lot of ways of drawing this circuit. I'm going to redraw it as this. This is the same exact thing. And then we'll have it come back to the battery. So these are in parallel. This current comes out of the battery, splits in three ways, comes back together. Okay, so the currents, we don't know if the current is the same. It could be the same, but we don't know that it is. If these resistors all had the same value, then it would be the same current. But they're all in parallel, so they have the same voltage. Again, we don't know about the resistance. The only thing that we know for sure is that the potential difference is the same. The voltage is the same across each. Now, if they had told us that these resistors are all the same, then they would have the same current going through them because they have the same voltage. But if this is V1, V2, V3, this is the battery, those are in parallel. They have the same voltage. Now, they potentially, no pun intended, could have the same current if they have the same resistance value, but they didn't tell us that it did, so we don't know that. Okay, so let's take a look at this example. We have a battery, and then we've got three resistors. So again, you could draw this, you can redraw this if you want to, but this current splits off in three different ways, and then it comes back together. So I1, I2, I3, this is I. Again, the wires don't have any resistance. You don't have to draw them like they drew them here. You could draw them the way that I've been drawing them, like I did in the previous picture. So these are in parallel. They have the same voltages. We want to know what current is provided by the battery. So to analyze this, we've got to make this into a simple circuit. So these three resistors are in parallel. Let's replace them by one resistor, one equivalent resistance. So in parallel, we know how to add together resistors in parallel now. And here we're doing it. 1 over 58 plus 1 over 70 plus 1 over 42. You get that, and then you take the inverse of that. So you can take those three and replace them by one resistor with a resistance of 18.1. So here's what our simple circuit looks like. 18.1 ohms. And then you can get the current from Ohm's law. So squiggly E is I times R equivalent. So then squiggly E divided by R equivalent turns out to be I. That's what you see here. So 0.66 amps. Now if you keep adding more and more resistors in parallel, the overall resistance goes down and the current goes up. So if you ever blow a breaker at your house, you have too many things plugged in, so the overall resistance is less. You're drawing too much current. Okay. Because the battery can't tell the difference between the original three resistors and a single equivalent resistance, the battery is providing 0.66 amps to the circuit. Okay, so whenever you have a parallel circuit, the equivalent resistance of any group is always less than any single one, as you just saw, right? The equivalent resistance is 18.1. That's less than any of these individual numbers here. That's just the opposite of series. Series, you add them all together, so the total resistance is always more than any individual resistor. Okay, so you just have more pathways, so the overall resistance is less. More and more different ways to flow. Okay. Oh, here's a nice analogy, actually. Driving in heavy traffic, if everybody was going the same way, there would be a pretty high resistance compared to if you have several different routes to take. So parallel circuits are several different routes to take. Overall resistance is less. Okay, good. So let's see what the current in this is. So we've already done this one, actually, I think. We've got 12 volts and 18 ohms. We figured out the total current before was 2/3 of an amp, if you remember. I times R equivalent. These are in series, so the equivalent resistance in series is 18. So then the current would be this divided by 18, and we saw this was 2/3 of an amp. Okay, so we've seen that one before. Now in parallel, the equivalent resistance, I'm going to do it the way that I do it. Do it up here. 1 over the equivalent resistance is 1 over 12 plus 1 over 6. So this would be 1 over 12 plus 2 over 12, so 3 over 12. Remember, that's 1 over the equivalent resistance. So 1 over 12 plus 2 over 12. So 3 over 12, and then you got to flip it upside down. So equivalent resistance then is 12 over 3. Everything is in ohms here, so 4 ohms. Okay, then if you want to get the current, that would be squiggly E over R equivalent. So 12 divided by 4. So 3 amps here. Okay, or if you prefer, you just do it in your calculator. R equivalent equal to 1 over 12 plus 1 over 6. Get a value for that, and then take the inverse of that. I just wanted to do it without my calculator, so I did it this way. It's the same formula, just written 2 different ways. I'm not doing anything different. Okay, good. So 3 amps here. So when the switch closes the battery current, what happens? So right now the switch is open. Here, the switch is open, so we only have current going this way. Now when you close the switch, the overall resistance of the circuit is going to go down, because now you've got 2 different pathways. The overall resistance goes down, the current is going to have to go up. Okay, as it says here. All right, excellent. So what current is supplied by the battery? I'll make this the last problem here. So let's make this into a simple circuit. We just want a battery and 1 resistor. Okay, so we're going to take these 3 15s, they're all in parallel with each other, and make them into an equivalent resistance. So the equivalent resistance, I'll do it the way the book has been writing it, 1 over 15 plus 1 over 15 plus 1 over 15. These are all in ohms, and then take the inverse of that. So you can do that on your calculator. So 1 over 15 plus 1 over 15 plus 1 over 15 would be 3 over 15, and then, as it says here, take the inverse of that. So 3 over 15 would be 15 over 3, or 5. So you could take these 3 15s in parallel and replace them by 1 5. So whenever they have the same value, 15, 15, 15, if you've got 3 of them, it's kind of a rule of thumb, the equivalent resistance is going to be 1/3 as much, if these are all the same. In this example they are. And then you can get the current like we did before. Squiggly E over the equivalent resistance. So 5 volts divided by 5 ohms, 1 amp here. 1 amp here, but also 1 amp here. Okay. Alright, so I'll be making a video for the second part soon, and any questions, just email me. Talk to you later. Bye-bye.